Yeah, I really appreciate y'all showing up and listening to me ramble for a little bit here. I wish I was there in person. That would be a lot more fun. But also, it's not that much fun to travel all the way across the state in the middle of January here. But first of all, let's see here. Oh, there we go. I thought I should say something about who I am, but I'll only do this very briefly. So I grew up here in Soldovia, where I live now. I'm a geologist. Soldovia is a little bit like Petersburg, fishing town, protected waters, off the road system. So I've been through Petersburg a couple times too. And I got into the subject I'll be talking about today, which is landslides and landslide generated tsunamis in the wake of a big landslide that happened in 2015 and went into the head of Fjord in Icy Bay. And so that's I've been at this about a decade. Prior to that, most of my work was actually more on the tsunami end and like earthquake generated tsunamis. I also, studied earthquakes and a little bit of volcanic eruption stuff. So a lot of geologic hazards kind of work. Today, what I'm going to do is I've got a couple of presentations that I gave actually at a scientific conference last month, and I'm repurposing those to a fairly significant extent here. And the main bulk of my presentation will be from those, and so that's partly apologies for not making something totally custom for you guys. That's something I already have put together, but it also gives you kind of an honest picture of where the conversation is in the scientific community about some of these topics. And one of the takeaways I hope you'll get is that there's a lot we don't know, and we're really actually fairly far behind the curve on this on the challenges of landslides and landslide generated tsunamis. And so you can kind of see, at some level, the state of the art here. And so yeah, I'll give a version anyway of my whole presentation on the Tracy Arm tsunami. I'll talk a little bit about the work I've been doing to map landslides throughout Alaska, which actually was it'll be just a part of the presentation I gave last month when I was at this conference in New Orleans. I'll briefly mention something about Horn Bluff. And the only reason I'm doing that is that when I was in Petersburg a few months ago, people mentioned concerns about landslide generated tsunami from Horn Bluff. So I won't say a whole lot, and it'll be mostly fairly reassuring. So that's the spoiler for that. Then I'm going to talk about LeConte Glacier a little bit longer. That concerns me a little more, not so much right now, but maybe what we have looking ahead a decade or so into the future. Yeah, so with that, this is the kind of headline note about the tsunami that happened back on August 10th is that it's the second highest tsunami ever recorded, which is not all that scientifically significant. It makes it really interesting. So this tsunami reached around 1,500 feet up the mountainside, and so it just falls a bit shy of the 1958 tsunami in Lituya Bay. Some of the work I'm going to be presenting reflects a lot of colleagues who have been involved in this, and in particular Dan Sugar, who's a Canadian geologist. He has been kind of the cat herder who's brought a whole bunch of these scientists together to kind of try to produce some preliminary analyses in what is fast for scientists anyway. We're only a few months away from when this event happened, and we're actually already in revisions for a paper that has a lot of the material I'll be presenting today. I also wanted to flag Pat Lynette, who actually was in Petersburg for the post-tsunami survey and also produced a lot of the modeling results I'll be showing, and Jackie Kaplan-Auerbach, who is a seismologist and did some really amazing work that I'll also mention in here. I want to kind of run through this somewhat in chronological order. So I'm going to start out with things that happened long before the tsunami, work my way up to when this landslide and the tsunami happened, and then talk a little bit about what happened after that. I want to leave a little bit of time at the end. I just kind of titled it How We Failed, and in particular, how did we fail to anticipate this event at all? And I think this is a really important question that me and my colleagues need to be asking if we're going out there trying to do something that's useful to people. It's pretty embarrassing to have something so dramatic happen and have it completely catch us by surprise. And so I really think we want to directly confront that. Before I get into that kind of chronological story, I want to give you some picture of what actually happened. So just kind of get that in your head. This is not actually a photo, as you're probably picking up. This is a model animation. This gray patch is a chunk of the mountainside at the head of Tracy Arm, south arm of Tracy Arm. This is Sawyer Glacier over on the right. And this is actually an animation that is moving right now. It's Pat Lynette put this together, and I asked him to make an animation that would run roughly in real time. Almost always when you see tsunami animations, they accelerate it a bunch, kind of in a hurry to get through what is showing. But I thought it was pretty interesting to see what this looks like if you actually let it play out in real time. And it looks like it must be in slow motion or something, but that's just because this is so enormous an event. So that chunk of rock that slid down here, the upper edge was at about 3,000 feet above sea level. And it slides down, hits the water, kind of acts like a piston and drives this big wave that goes up onto the glacier. And we know this definitely really happened. We have good evidence of that. And then the tsunami sweeps up the slope in the foreground here. And it's right here in the foreground where it reached somewhere around 1,500 feet of elevation. We don't have the most precise estimate yet, but it's around that elevation. And then this wave propagates off down the fjord. So that's what caught our attention. But now, if we go back in time a little bit, what were some of the things we might have been watching over different time scales leading up to this landslide? So I have this figure, and this will kind of come back over and over again as I put different things on these timelines. We're looking at everything from decades, months, days, hours before the landslide, and then similarly going into the future. And the first thing I want to note is episodic glacial retreat. And so these are periods of glacial retreat that happened in Tracy Arm over the years before this landslide. It actually, and I should have probably plotted that previous one with they're actually quite short periods here. The most recent one prior to 2025 was in 2016, but then 2025 there was quite rapid glacial retreat, and there was some glacial retreat actually that seems to have been directly caused by the landslide. So if we kind of put this on a map here, this is Tracy Arm, kind of the upper part of Tracy Arm. You've got the North Arm here. South Arm is down here. So the landslide happened down at Sawyer Glacier on the South Arm. And if we were to go back to, I use this acronym here, LIA, this is Little Ice Age. So this is not the big ice age that filled everything with ice. This is just the most recent time when glaciers advanced. And in many places, they reached their maximum in about 1850. We don't know exactly where the Sawyer Glacier was in 1850, but it may well have been right here. This fits with the information we have. By the late 1800s, it had retreated back into this area. We have photos from 1948, so we can see it kind of working its way backwards. And this continues towards the present. It actually stabilized for a number of decades right here, and then went through rapid retreat, then stabilized again for over 10 years, then rapid retreat, stabilized, and then went through retreat this year. And so there's that last episode of glacial retreat there. So if we want to look at that a little more closely, this is a photo from 1978. And these yellow outlines here, this is the slope that eventually will fail. So right here was, pretty deeply buried in ice in 1978. By 2012, the ice had fallen back, I think about a mile back up the fjord, and actually gotten fairly stable again at this point. The ice would move back and forth a little bit. The ice front would move back and forth a bit, but staying roughly in the same place all the way through until this retreat event in 2016. And then it retreated back to this point, so getting pretty close to our slope that eventually is going to fail. And then in 2025, so this is a picture from June 22nd of 2025, you can see the ice went from being right here, and it's now started to retreat. So it's kind of fallen back into this space. This is, these are scientific figures, so it's all in meters, but this would be like 600 feet or so of retreat up to June 22nd. As the summer went on, we don't have more high-res images before the landslide, but it initially kind of bit out in the front. And in early August, this piece of edge fell away and it retreated here. But the last photo we have, I think about a week before the landslide, it showed the ice face right about here. So right about in the middle of the chunk of slope that then failed on August 10th. And so this came down, it sheared off the lower part of the glacier, produced this tsunami that actually went way up onto the ice up here. This is debris moved by the tsunami, and caused the glacier to calve really dramatically up here. And this is a big like cliff on the ice face where the ice fell off. So that glacial retreat was furthered by the landslide itself. One thing that we don't see prior to this is any signs that the slope was deforming for years prior to failure. And this is something that geologists like me spend a lot of time looking for. It's kind of the standard approach trying to figure out where big landslides might happen as you look for signs of slow deformation. This is one data set that there's nothing really interesting to see here because we didn't detect anything with this approach. There are other techniques we used as well, and other than some evidence from just a few days before, we don't see any really substantial motion. The only exception to that is there were a couple of small landslides in the area. There was one back in 2017 and one that happened just like a month before the big landslide. So if we'd been really watching closely, we might have said, I don't know, I get a little worried anytime I see, it's a small landslide. It would be a huge landslide if you're standing there, right? But not nearly as large as the one that ultimately happened. But generally, the slope wasn't showing us a lot of signs that it was up to something dramatic. Now, there was a lot of rain in the last few days before the landslide. And so this is just one graph of rainfall. And you can see that that landslide occurred during a period of several days when it was raining over an inch, sometimes over 2 inches a day. Now you guys are all from the area, so you kind of know this is not like record breaking, right? These are very rainy days, but they're not necessarily that extraordinary. There's a reason that I think they may not actually be all that important at all, that this may be somewhat a coincidence. This is a record of seismic activity prior to the landslide. And one of the things that was really dramatic about this landslide, it's something we've seen for other landslides, but I'd say for Tracy Arm, it's the most dramatic example, is that there were small earthquakes that were produced by the landslide before it failed. This shows the last, I think, 36 hours or something, 38 hours, I guess, before failure. And it's just kind of counting up these earthquakes. So there's hundreds and hundreds of these earthquakes. If you look at this graph at the bottom here, it's just kind of a bar graph showing those earthquakes. Jackie Kaplan-Auerbach, who did the analysis of this, and she has local connections too. She knows the area. She found some earthquakes that extend all the way back to 6 days prior to the landslide. And she can tell they're related because they have the same kind of wiggle shape. Basically, the vibration that was produced was the same for these early earthquakes. So even though the rain started before the landslide, the earthquakes started even earlier. And those earthquakes, as best as we understand, and we're definitely getting out here to the edge of what we understand with landslides like this, once those have started, that landslide is pretty inevitable. So even though that rain came in, it was really, it might have been inevitable already that landslide was going to happen. So yeah, there's these, two in the few days before, a couple weeks before, we have the seismic activity that starts first and then some rain coming in later. So that brings us up to the landslide itself. And so I'll go ahead and show another animation here. This one is sped up. I forget if it's 10 times faster than real time, but it gives kind of a little chronology of the tsunami sweeping down the fjord. I hope this is coming through with Zoom. I know sometimes it can get stuttery with poor internet connections and stuff. But the tsunami generated up here initially it's a really big splash, and I'm getting an echo from someone now. But but it organizes itself into a wave. And one thing I want to point out is the wave breaking that happens here at the lower end of the north arm of Tracy Arm. And you can see there's all of this white is reflecting that wave breaking. The reason there's all this wave breaking here is partly it narrows, the wave gets kind of funneled in here, but it's the biggest factor here is probably the shallow water. There's a relatively shallow area. It's kind of well known by mariners in the area, not to my knowledge, not so much because it's a hazard, but because it's a place that's actually shallow enough to anchor. So it's attractive for staying overnight there. So I want to talk a little bit about some of the close calls that happened in the minutes to hours after, or well, that are guess in it could have worked out really differently. I guess what I'm trying to say. So one of them, I know Alyssa and Jim are there in the room. The Dauntless was anchored on that shoal 24 hours before. That would have been a really, really terrible place to be in the tsunami. There was probably a breaking wave that the breaking portion was easily 100 feet tall. We saw places where the wave ran 300 feet up the mountainside right next to that shoal. So a really bad place to be. Even closer call is this small cruise ship, the National Geographic Venture, which was actually going up the fjord at the time. And they experienced the tsunami. They saw wave breaking on the shore, but they were in really deep water at the time, further out Tracy Arm, and so it wasn't too big a deal for them, and they decided to just keep going. And so they cruised on up the arm. They crossed that same shoal we were talking about something like an hour or two later. So if that tsunami had been an hour or two later, then they would have been right in that particular place. I would also say that in hindsight, it probably is not a great choice to just keep cruising when something like this happens. There are cases where one landslide happens and then another one follows right behind it. So it's pretty scary, I think, that all of these people were right up in that area. So there were some impacts that were further away than those animations I showed. And here's one more animation. This one's sped up even more, and we're zoomed way out. It has a couple of color shifts in it that are kind of confusing. But by the time the wave passes out of north and south arms here, it's actually pretty gentle. It's still, surprisingly tall, but it's not breaking very violently. You don't see many impacts along the shore here. And you might think, oh, we're now beyond all the action. But a couple things happen. One is that the wave actually goes out and impacts the island here. And that's where you may have heard about the kayakers that were almost hit by the tsunami there. But another really interesting thing is that the tsunami actually focuses at the head of Williams Cove. So while out here you can hardly see evidence of the tsunami, when you get up to the head of Williams Cove, the place has been really smashed. And the tsunami reached about 100 feet up in the forest back here. And so we went and did ground survey in this area. So it's a pretty extreme example of tsunami focusing. One, I guess, scientific piece of good news is that the model predicts this focusing quite well. So we actually know well enough how to model tsunamis that even though this is non-intuitive, if you're just like, wandering around taking a look at things, the models can actually predict this sort of thing. So another really interesting phenomena that happened in the wake of the tsunami is called a seiche. And so a seiche is a harmonic wave. If you think of like water sloshing back and forth in a bathtub or something like that, it is a wave that has a regular period that matches something about the basin that it's in. And we've seen this a few times with tsunamis. It's actually common to have some kind of seiche happen in the wake of any tsunami, but the one here was quite unusual. This data here is actually nothing to do with water level measurements or any direct measurement of the wave itself. It's actually seismic data from the entire northern hemisphere here. And what we can see in the seismic data, it's shown by this bright line here, is that there is a seismic signal, like a sound basically, coming directly from Tracy Arm, and it has a period of about a minute. It's actually slightly over a minute, I think 66 seconds or something like that. And so there's some sound coming out of Tracy Arm that is, so low frequency we can't even, it's not even close to what a human could hear, that every 66 seconds things oscillate. And this lasts for over 30 hours after the tsunami. So, if you think how many cycles is that? Well, it's, 30 some hours times 60 cycles. This energy stayed in here. This actually proved a quite difficult thing for Pat Lynette, was the main person who worked on modeling this, for him to actually recreate, but he did figure this out eventually. The model is down at the bottom, and we can actually confirm it with this very messy looking satellite observation. But if you kind of squint, kind of blur your eyes, you'll see there are these red patches and blue patches in here. These are areas of higher and lower water measured by a satellite that happened to go across Tracy Arm, I think around 5 hours after the tsunami. And this pattern of red and blue patches, you see, matches this model recreation as well. Now, this is one thing that's quite surprising about this, is that the seiche is actually stuck out in this part of the fjord. So it's totally separated from where the tsunami came from up here. It traveled out, and then in part because this part of the fjord has these two kind of curved ends on it. So if you imagine a wave kind of bouncing back and forth, it actually goes around the corner, bounces off again, comes back, bounces off this, and it bounces so efficiently that it's able to last for over 30 hours in this setting. So this is just, I don't know how well this will come through, but this is an animation of that effect. Some of the other stuff going on in here is these weird round circles. Those are actually at least a somewhat real feature of the modeling. They're basically big whirlpools that just kind of sit there and take hours and hours to dissipate. The Nat Geo Venture, when they went up the bay, they described hitting strong currents that caused them some navigational difficulties. It's quite possible that those were some of these eddies like this that persist for a long time afterwards. They can be a navigational challenge for vessels because they turn the vessel really rapidly. So we also have a lot of field observations of this tsunami. We got reports from vessels that even experienced the tsunami. There's the Nat Geo Ventures account. There were vessels that were outside the fjord, but still experienced quite large waves. One of them was friends with my colleague Jackie, and so within half an hour of the event, they were talking on the phone about the tsunami they were observing. And people traveled up the fjord in the days after the tsunami. I would say I would do that too, because I would be super curious, but there is a risk to going back into a place, and that risk does persist for some time. We do sometimes see landslides, like I said. You can have one big landslide like this, and then another one might happen anywhere from, minutes to months later. So, it's something to do with eyes open at the very least. USGS actually got out just 3 days after the landslide and did a really excellent overflight. This is one of their photos. We're looking straight down the landslide scar, which has this really sharp kind of corner in it here, from the kind of chunk of rock that's sort of clinging to the top of the slope 3,000 feet up. And so we can see, the area that was hit by the landslide. We can see evidence of the wave up on the glacier, including all this crushed ice trapped between the crevasses. We can see the forest stripped by the wave over here. They took a really fantastic set of photos. These are all available online. And Pat and Alyssa and Jim were out there October 12th to 16th, along with a few other colleagues. Some post-tsunami survey done. This was supported by the National Science Foundation, or we still are waiting on them to fully come through, but we've been very much assured that it will happen here and pretty soon. But the NSF RAPID program, which basically supports people going out and doing surveys in the immediate aftermath of disasters. Some of what we did was what I would think of as a very standard thing to do after a tsunami, which is to go out and measure how high the water got. And the reason we do this is that that is the most basic parameter that you can try to model. And tsunamis like this are still, there's still a lot of challenges in modeling them. So data like this can really help us better understand what happened. This model kind of goes both ways. It's both a matter of getting the data in order to test the model and improve the model so you could, try to model something that hasn't happened yet and have some confidence you're doing it accurately. But it also allows us to better understand what happened by seeing where the tsunami was higher or lower. We can see what sort of a modeled wave would actually lead to those effects. So there's a lot of value in that. This is something that I've been involved, Pat and I have both been involved in a number of a number of post-tsunami surveys like this. One thing that I was personally kind of spending some time and really interested in was the idea of finding evidence that might help us tell things like how strong the current was going when there was when the tsunami was happening. And so things like the trees that are tipped over up in Upper Williams Cove. I documented places where lichen had been stripped off rock on Sawyer Island by the tsunami. There's also a lot of torn alder leaves. Now they're also wilted here. We were there as, the leaves were naturally dying in the fall, but this is a very unusual pattern of leaf damage. If we could recreate that in the lab, picture literally taking a hose and squirting it at an alder leaf, we might get some constraint on how strong the current was, which is a much it's an added level of detail on what we would try to model in a tsunami like this. So we can skip this one. This is really for my colleagues at the conference. So I wanted to take a moment, as I mentioned, to talk about how it is that we failed to anticipate this event. Speaking for myself, I had actually looked at Tracy Arm years ago, like 2 or 3 years ago. There was a landslide there in the 1990s. I mapped that. I, stared at a bunch of satellite photos and didn't really see much. Moved on to other places. We've got the USGS landslide program, the state of Alaska landslide program. Neither of them had flagged Tracy Arm as a place of concern. And I would say, unfortunately, that this is not really the exception. It's more the rule that with natural hazards, and especially including landslides, geologists get surprised a lot. I sometimes feel like a bit of an ambulance chaser. Something dramatic happens and then I go study it, but that doesn't really do much good if that dramatic event was a direct danger to people, as this one was. So, hopefully we do better next time, right? But how many times are we going to say, hopefully we do better next time? So I've been thinking a lot about what we might have done better. We do have every reason to think there will be further events like this somewhere. And this isn't like who knows, maybe, we had one in 1958, we had one in 2025, maybe there'll be one in the year 2100 or something like that. Actually, these have been happening a lot recently. The most recent dramatic event prior to Tracy Arm was in 2024, just a year earlier, in Pedersen Lagoon. This chunk of material here slid down, went into this lagoon, generated a tsunami. It had about 200 feet of run up just around the corner here. It swept out of this lagoon into the next lagoon, across that lagoon, and swept underneath occupied guest cabins at a lodge here. So another close call. Again, we got lucky. It swept through a campsite over here, picked up the bear box and swept it away. Still, nobody was there, so it worked out okay. If we actually go through and start really systematically documenting these, this is just one way of doing that, and I'm happy to talk about this in more detail. But it seems like there is a big spike in these events just in the last couple decades here. And so I really think we're going to see more of these, and quite soon. This isn't we've got decades to kind of figure our act out here. We really need to do better now. I think maybe one of our mistakes is that we're focusing too much on the signs of slow deformation. It's an important thing to map. It's something we should do. I'll talk a little bit more about that in the next section of my presentation today. But it is using it exclusively as our way of understanding where landslides will happen. Well, it certainly failed in this case, and I think I would say we were likely to keep missing the mark if that's all we're doing. One thing I think we maybe should pay more attention to is patterns of glacial retreat. And in particular, this pattern where we see a glacier that stabilizes at some point and then goes through another period of rapid retreat. And I'm happy, like, if you want to hear me elaborate on that and why I think that particular pattern is concerning, definitely ask me at the end. I can ramble on at some length with that. But just as far as something that's directly observable, if we see a glacier, retreat for a while, kind of stabilize, things seem okay, and then it starts retreating again, those ones particularly worry me. This map I threw together at the last minute, so it's not a very nice map, but we're looking at all of southern Alaska here. So the Kenai Peninsula is off at the left here. That's Tracy Arm there with 2025 written next to it. These are all the glaciers that are tidewater glaciers. And the ones that are marked in red are at least close to the most retreated they've been in the last 100 years. So most of the glaciers are in that state. It's not that many. We're looking at 25 or so glaciers. Well, the dates here, these are all landslides that generated tsunamis on those glaciers, at the fronts of those glaciers. So we have 4 out of 25, and 3 of those happen to be just in the last couple of years. So that's a really worrisome pattern. It may be that the likelihood of these events is much higher than we appreciate. So, okay, I'm going to transition here. Let's see, I burned through a half hour there. I'm going to try not to ramble on too long. And I want to talk a little bit about landslides more broadly in Alaska. And I've been spending a lot of time mapping landslides throughout Alaska. A lot of this is a matter of like staring at satellite imagery. There are quite a few of these that are things that have been sent me by pilots and boat captains and this sort of thing. People who are out there and observe things. I'm exclusively mapping the biggest, most dramatic ones, partly because they're the easiest to find. Alaska's a big place to look for this sort of thing, so it makes it more tractable. A lot of this, the inspiration for this really comes from work that I was involved in looking at a large, slow landslide at Berry Arm. And so this is a giant mass of rock that, especially about 10 years ago, was creeping towards the fjord. And it did actually experience a significant but not tsunamigenic landslide in 2020. And lately it seems like it's mostly calmed down. But one of the big surprises in kind of the process of discovering this landslide is that it was super obvious. Like, it did not take any, high-tech analysis or proprietary data or anything like that. You could go to data that was publicly available all over the place and see evidence of this landslide quite easily. And yet, none of us geologists had noticed it. And so one of the takeaways I had from that is like, maybe we just haven't been looking enough. And so that was a big piece of the motivation for me to start looking around Alaska. And I was looking both for slow landslides like this that might move, inches per year, they might move tens of feet per year, and also catastrophic landslides. And so these are ones like what happened at Tracy Arm. They're moving, probably faster than you can run. So a very different kind of deformation. Some of this is motivated. I mean, definitely initially the motivation was just like, let's see what's out there. What should we be paying attention to? However, where I've been focusing lately is on the idea that as geologists that we use to try to understand how a slope goes through a process that ends in a catastrophic failure. And so there's this idea, we call it a landslide life cycle, that you start out with a slope. We're talking about bedrock slopes in this case. For them to be this large, it really is not just a matter of soil and such. a bedrock slope that's just sitting there, able to hold itself up. Something changes. For instance, maybe glacier retreats at the toe, permafrost thaws, earthquake happens, and it starts deforming. And so cracks form in it, and then those over time lead to a slow landslide that has a really well-defined crack along the base, and then boom, it fails catastrophically. Now, this is an idea of how these work, but it turns out that there's very little test by scientists of whether they actually work this way. So this is assumed a lot. For instance, if you're in Norway, there's a lot of energy put into monitoring landslides. And they make a very strong assumption that those landslides are going, the catastrophic landslides that might generate tsunamis, that they're going to happen in a place where a slow landslide is happening. People are making the same assumptions right now, trying to assess this hazard in Glacier Bay and in Prince William Sound. And so as I did all this mapping, I thought maybe I should try to check to what extent this really lines up with reality. And we can kind of think about a few really specific questions we could ask. And I won't dive into these in full detail. I'm happy to talk about them if you like. But basically, if things behave this way, well, then there's a number of different directions we can go, such as assessing where landslides are likely to happen by looking for slow deformation. And so my thought is, to test this, I should just look around, find places where big catastrophic landslides happened, and look at satellite data and such from before to see what happened prior to that. And also, I should find slopes that seem to be behaving in the way that we would think could lead up to a catastrophic landslide, and see what happens. Watch them for a few years, or, again, looking back through time with satellite imagery, and see what happens. So that's one way of kind of thinking about the inventory that I've done. And so, as I mentioned, this inventory includes very large landslides. So this is over 1 million cubic meters. It includes slow landslides that are experiencing what I call obvious creep. So this means that they are moving more than 10 feet per year, basically. And there's one particular way that makes it relatively easy for me to find them. Or they were not creeping at all. They failed catastrophically. So this is like a nearly instantaneous failure, like the one that happened in Tracy Arm. There's a bunch of other landslides in there that I looked at because they might have met these criteria, but they don't. I keep them in inventory anyway. So just as an example, here's a place where there's a slow landslide. So this arcuate cliff back here is outlining a chunk of rock that has been moving along slowly. We don't know exactly how fast. This one fails to meet my obvious creep criteria. However, in 2021, during a big rainstorm, this landslide failed catastrophically. And when that happened, you can't see it in the source area now, it's in the shadow, but you can see the effects of it. It came down, it banked off the far side of the valley. So this is kind of the edge of the landslide as it slid along. And it ended up in this area. This is the landslide deposit here. There are these two little lakes that were there before. So it pushed those lakes out and formed a tsunami that flattened the forest all through here and actually swept enough boulders and debris into the Alsek River to shift the Alsek River over somewhat. So this one does qualify for my inventory because of that catastrophic failure. Another example would be, this is a landslide that is experiencing what we would call obvious creep. And I hope it's coming through well enough. I'll play it a couple times, but you will see this area in the middle. It moves to the left and up a little bit. And so that starts kind of at the end around 2021. This huge area of mountains starts moving. Similarly, this is another creeping landslide, a very different type. It's flowing more in a viscous way out into this valley bottom up in the Brooks Range. So all of these would be landslides that were in my inventory. So when we start looking at this, it turns out we get some answers to the questions I was asking. One way of organizing it is in a Venn diagram. So everything in this kind of roundy edged area here, these are all the slow landslides. And this box has all of the catastrophic landslides. And so the big take home from this is the overlap is not that much. Most of the catastrophic landslides, I can't find any signs of precursory creep. And really, there's a lot of landslides that are moving along slowly and not failing. So the overlap is a lot less than I expected, certainly when I got into this. This applies even in areas where we see some of the kind of state-of-the-art studies where they use satellite data that there's a technique called INSAR, which uses satellite radar to detect slow-moving slopes. And so those detected what's in the dashed lines in these two cases. And then I went and further mapped other stuff in this area. Mostly, they're not catching the ones that fail catastrophically. So this is, a fairly, I think, a really important thing to be aware of, that catastrophic or slow landslide behavior, the slow creeping landslide, is not necessarily as strong a predictor of catastrophic landslides as we might have thought. The good news there is that when you see something creeping slowly, it may not be as likely as you think that it's going to fail catastrophically. The bad news is that if we rely on detecting slow motion in order to anticipate where catastrophic landslides will happen, we might miss the mark. Okay, so I want to transition again here. Apologies if this talk seems like it has some corners in it. And now talk just a little bit about your own backyard there in Petersburg. And so I don't actually have a good slide for, oh, I'm getting an echo again there. I don't have a good slide for the, Horn Bluff, but I did want to address that for a moment. As I mentioned, when I was there in Petersburg, I heard people say there was a lot of concern about this. And I mean, certainly it's a steep slope above water. It does show some signs of rockfall activity and such. So at some level, there probably is at least a nominal level of risk there. I would say that I've looked through what data I can get, which is far short of going out and doing thorough field work or something like that. And I don't see very many of the risk factors that I usually look for. For instance, I don't see the slow deformation. As I'm noting, that doesn't always forecast these events. But I think, if people are interested locally, I'd love to find a way to study that more and kind of check into it. But overall, my geology from afar would say not super worrisome. I'm going to see if I can figure out which one is echoing on me and mute it here. Oh, now it's not echoing. I wanted to also talk about LeConte Glacier. Actually, I've heard I've been asking around, and some people are like, you pronounce it LeConte. Some people you pronounce it LeConte. Some people say you pronounce the ferry named after it LeConte and the glacier LeConte. So anyway, I'm going to use LeConte for the moment. Feel free to correct me. In the wake of the Tracy Arm landslide, it seemed like, well, we should take a look at what's going on here. And so I've given it kind of a once-over, just trying to understand what's going on with this glacier. So first of all, we can go back in time a little bit. This is an image from 1979, and we can see that from 1979 to 2017, it retreats, a mile or so. Up the fjord. And I looked through, there's one older image from the 1940s, and it's a little further out in there. So we see this kind of very modest retreat over the last almost 100 years. There's not a lot of retreat going on right now. And I'm going to jump out of my presentation here, and we're going to go for a little bit more kind of you're going to get a closer look into my brain at the sorts of things that I'm looking at. So this is an animation with one image per year over the last 10 or so years of the terminus of LeConte. And before it gives someone epileptic seizures, I'll pause it here. And basically what you see through this is back at the beginning, we see a little bit of retreat, but then we actually see it advance again. So by 2022, it had advanced a bit, and then we see that kind of falling back just a little bit. I think, yeah, it's back a bit in 2025. Overall, this is the kind of normal variation that you see in a lot of glaciers. So I think that's good news. As I've pointed out with Tracy Arm, I really think rapid retreat is a worrisome sign if you see a glacier doing that. However, bad news here is that I don't think this is likely to continue. I think it is likely to go through rapid retreat in the not too distant future. And I can't put a precise time frame on that, but it wouldn't at all surprise me if it was less than a decade. So talking, in coming years. So one piece of evidence that we have to look to is glacier thinning. And so this is a data set showing, it's for all glaciers in the world, showing the way the elevation of the ice is changing over time. Let's see, I'll zoom out a little bit so you get a little more context. The parts that are red, the glacier is getting lower. The parts that are blue, you see some little patches here, are getting higher. Obviously, the story is pretty red in general. This is LeConte here. And then there's, I think this is Shakes Glacier. And then I believe this is called like Divide or something like that. So what we see is kind of modest thinning along LeConte Glacier. That's enough to eventually drive retreat, but it's not super fast. However, this dark red color in over towards Shakes, this is really rapid thinning. And so this is the sort of thing that that can lead to really rapid retreat. And if we jump over here to, this is the Shakes Lake terminus of Shakes Glacier, we see steady retreat in this area. One thing that I thought was useful to look at was to look at the point where that kind of pool of ice between Shakes Glacier and LeConte Glacier, where they come into contact. And so this is, again, one of these animations. It's one per year, spanning about a decade. And what you see is that in the last few years, LeConte Glacier has started oozing into this pool of ice on the other side. So historically, this was a source of ice to kind of feed LeConte Glacier. Now it's the opposite. It's actually LeConte is losing ice over into this area. And I think that is likely to just increase with time. And so not only is LeConte thinning to some extent just of its own accord, it is going to start getting starved by ice that's falling into this adjacent basin. And I think this basin will probably grow pretty quickly. And so what I'm, really, I want to be super clear that this is all very much developing science. Like, this is not like, oh yeah, there's a standard way to approach all this stuff. We could easily grab a colleague or two of mine and you could hear some significantly different perspectives on this stuff. Potentially even heated debate if we really found just the right spicy colleagues to line up. So I don't want to give you any impression that I like absolutely know the answers here and I'm just coming in as an authority. I'm trying to explain what I'm seeing as I look at available data here. And with what I'm seeing, I think it is likely that we will see this current front of LeConte Glacier start retreating and fall back into some distance up glacier, probably a mile or more up into this basin behind, in the not too distant future. And when that happens, I think it's worth really paying attention to that. Like, I think we should treat this as a very worrisome behavior in a glacier when it goes through these periods of rapid retreat. This is what we saw at Tracy Arm with South Sawyer Glacier, but it's also Surprise Glacier had a big landslide that was associated with rapid retreat last year. I noted Pedersen Glacier. That one, it's not quite as straightforward. It went through really rapid retreat, and then a few years later, there was a big landslide that was slightly up the glacier. We see Grewing Glacier landslide in 1967. There are many of these cases, many of the biggest, most dramatic, and most tsunamigenic, that produce the largest tsunamis, landslides. They are happening right as these glaciers fall back and retreat really quickly. So that's something where if I was in the area, kind of spending time near LeConte, I would really flag it if we start seeing it retreating more quickly. All right, and so I will. Whoops, I'll go ahead and leave my thank you slide up there. But in case someone wants my email, I'll go ahead and stop there. Yeah, really appreciate your time, and I'm really happy both to take questions right now, and if you want to talk further, email or whatever. I'm very happy to continue the conversation and see if we can figure out useful stuff to do here.
Thanks so much, Hig. Can you hear me?
I can.
I've got a question. I'm going to start us off if you don't mind. Is
Sure.
it worth, so given what you just showed us about LeConte, is it worth or even possible to model a tsunami generated in LeConte and what its impact might be out further into Frederick Sound?
Yes, and Pat Lynette is like the perfect buddy to have for that question. He has made a lot of progress in being able to deploy models really quickly. And so, if he has the data to inform that model, he can build something quite quickly. And I think he also does a lot of this just pro bono. He's the sort of person where if you ask nicely, you might get a result rather than having to pursue a large grant or something. The main thing that he will need, and I would be, happy if there's work to be done here, I'd be happy to at least talk about how we would scrape that together. But is good bathymetry and at least low elevation topography. You don't need the high elevation stuff, but you need some kind of topography and bathymetry. And I don't know what all is available there. But if you have that, then you can do modeling. Now, a big caveat is you have to know what to model in detail and say like this is a very specific scenario that would unfold. You would need to know what the landslide was, and that we don't know in advance. However, it's still useful to throw some tsunamis out there, see how they behave, see what areas get hit particularly hard, what areas seem to weather a lot of different tsunami scenarios. And yeah, I would love to yeah, help make that connection with Pat and see if we could work that kind of thing out.
So any questions from this room here? And then would you let Hig know who you are as you ask the question, and what your connection is?
Yeah, this is Dave Ellis. I was curious where you measured the rainfall that you're connecting to this rockfall.
So, in the case of Tracy Arm, I should know the answer of that to that right off the top of my head, but it was a colleague of mine that compiled that. It's obviously not right there at South Sawyer. There's no rain gauge there. I'm trying to think where this one is, but it's probably something like Juneau or something. It's a ways away. I'm going to be doing a little reanalysis of that using a different kind of data that is more specific to Tracy Arm, but has different caveats. It is model data for one thing. It doesn't, it kind of like takes all of the weather observations and uses a model to try to figure out what was between those observations. So you can say something about the head of Tracy Arm. So that's something I promised Dan Sugar, who I mentioned as the lead author on this paper that's going on. I promised I'd do that over the weekend. So it's a little too early for me to have done that.
Yes, our incredible microclimates around here would indicate you need about 1 million rain gauges somewhere to figure it out.
Yeah, that is definitely one of the challenges. And actually, so there's both the, general variation related to microclimates. That's absolutely part of it. And the other thing is often elevation matters a lot. And most of the places where you measure rain is down low. And so there are people at UAF and DGGS at the State Geologic Survey that have been trying to expand, at least somewhat expand the number of weather stations that are up higher, simply because we really don't know how the weather down low relates to the weather up high. They're in these mountainous environments, it gets very complicated. And so there are a lot of uncertainties in what we know about rain.
Thank you.
Other questions in here? Hey, can you see the chat pretty easily from where you are?
I can do that. I don't have it up right now, but I see there are some.
Yeah, maybe you can just do those yourself.
Let's see here. There's a question from Toby Bakos. Has Baird Glacier in Thomas Bay to the north of Petersburg been looked at in regard to potential for similar landslide causing tsunami? Baird has retreated from its most recent terminal moraine since around 2005 and now has a very large lake, which is probably somewhat tidal in front of it. So the basic answer, the best short answer to has this been looked at in detail is no. There really is. So there's two levels to that. One is that most of the looking that has been done has been focused on looking for slow landslides rather than looking at glacier fronts. So that's issue number one. And number two, there's really like, if anyone's looking at the glacier fronts, it's me. And I did actually look a little bit at Baird Glacier, and I won't say I have anything profound to say about it, but it did jump out at me as one that's going through some retreat. When you have lakes like this and lagoons, this can absolutely be a really big hazard, especially right on the margin of that. The shoal and the slough and stuff that it would have to go down in order to reach the ocean would dissipate a lot of energy if there was a tsunami that was generated within that lake. I'm saying lake / lagoon. It sounds like it's, maybe close to tidal. I often, for my own kind of risk assessment because I like going out in the wilderness and visiting these awesome glacial environments. One of the things I do is I really try not to camp in any place like that, because when you're asleep, you're a lot more vulnerable. And you also spend a whole bunch of hours there. And ultimately, the amount of time is proportional to how much exposure you have. It just increases your exposure. So I really try to give these places, visit these places more briefly, because the risk level, I think, is quite high on any of these retreating glaciers.
Are there any others there in the chat?
That was the only question in the chat there. There was a technical question. Hopefully. Oh, here we got another one now. Can you summarize how a catastrophic landslide at Horn Bluff might affect Petersburg? So this would be another thing we could best address with the help of someone like Pat, who could do some modeling. So one of the challenges here is you pretty quickly get into this discussion of like, are we talking about worst case, or are we talking about likely? This kind of range from the really most probable events to the least probable but worst ones is really big. And so to give you some sense of that, I mentioned 4 landslides that have happened in the last decade that have caused tsunamis that have been right at glacier fronts. And if you looked at images of the landslides themselves, you can say, well, some of them are bigger and smaller, but they all look kind of similar. They're all like a big chunk of the mountain failed and went in. 3 of them produced really dramatic tsunamis. However, the 4th, barely even detectable. And it's a case that it's smaller than Tracy Arm, by a fair margin, but it's not small enough that it's too small to produce a tsunami. As best as we can tell, it was moving just a little bit slower. So the speed that the landslide is going ends up being really, really important how big a tsunami happens. Basically, if the tsunami or the landslide is going slow enough that the water can kind of flow around the landslide as it goes, then it doesn't produce that much of a tsunami. But if instead it hits it hard and kind of produces a splash, it kind of has that pistoning effect, then you get this very large tsunami. So that would be one of the sources of uncertainty, that even if we had that model sitting in front of us, we would have to be really clear that, you might get a landslide that looked a lot like something that you had in your model. The model might show a big tsunami, and yet the tsunami might be small. So there are a whole bunch of caveats that we'd, want to be really careful about thinking about in that case. What we see when we do model, call it a very bad case for something like Horn Bluff, is that the tsunami is very directional. And so if you look at places, if you're standing on a shoreline and you're looking directly at Horn Bluff, that would be a more vulnerable place. If that tsunami has to go around some corners and such, it may be dramatically smaller. So some of the impacts from this type of landslide generated tsunami are highly localized at those areas. To go beyond that, we would have to go to modeling that hasn't been done yet. It is feasible, and yeah, I think that might be a valuable thing to do.
Deep was the water in Tracy Arm at the foot of that slide?
Yeah, so it's kind of an interesting question because we don't have direct measurements of that. The arm had been mapped, but not all the way to there because this was an area that it was just retreat this year. So in the modeling efforts, there are two different modelers, Pat, who I've mentioned a number of times, and another colleague of ours, Katie Barnhart at the USGS. And so as the first data came out, they were like, all right, so let's try to model this tsunami. And they just had to guess at what the depth is. So they tried some different things, and they could not reproduce the size of the tsunami until they increased the depth. And I think they ended up with around 500 feet of water depth, if I recall correctly. And I could, if you email me, I can double check that and try to get the exact number. But they had to have quite a bit of water in order to produce a tsunami that was as large as what we saw and also had the particular pattern of run up down the fjord. So we still don't have direct measurements of it, but based on the modeling, we think that might be ballpark correct, somewhere 500 plus feet deep.
And that 500 feet absorbed the whole 3,000 foot stack of rock.
Yeah, well, so this again, without doing a bathymetric survey, which I hope will happen eventually, we don't have direct observations, but I can speculate a bit about what happened. So first of all, it's 3,000 feet tall. It's a lot less thick. It's still quite thick. It's like 500, 600 feet thick. So it's a very thick sliver of rock, 3,000 feet by, call it 500 feet. It slid down into the fjord. Well, we know it was moving really fast because it generated this huge tsunami. I think that it's somewhere around 100 miles per hour. It's going quite fast. When a chunk of rock is moving that fast over rough ground, it breaks up. Also, when a landslide like this goes into a fjord, there's all this mud on the bottom of the fjord that can help lubricate that landslide. So commonly what we see is that landslide keeps traveling down the bottom of the fjord, and it spreads out for miles down the length of the fjord. Most of the tsunami is generated really quickly at the initial impact because that's where the landslide is moving fastest. And then once it slows down a little bit, might still be affecting the tsunami to some extent, but it's a pretty secondary effect. But that landslide can keep moving and it can spread itself out, and so it doesn't necessarily leave just this big lump at the bottom of the slope.
Yeah.
There is another question that somebody asked in the chat.
Oh, yep.
The answer.
It's popping up for us. Hey.
Sure, I'll read it out loud here. So you mentioned multiple earthquakes prior to the landslide in Tracy Arm. They weren't noted by the Tsunami Warning Center, but by the Alaska Earthquake Center in Fairbanks that tweeted this. It was their gauges nearby the glacier. Boaters are looking for tsunami warnings through NOAA. Will AEC begin to join forces with NOAA? Okay, there's a number of interesting details here. So there are two different seismic signals to think about here. One is what I was talking about primarily in this. Well, actually, there's three different ones. So one is this precursory seismic signal. These precursory seismic signals. So these are earthquakes produced by the slope before it fails catastrophically. Then there's the landslide itself, and that produces essentially a big earthquake. However, it's not. It's different in wave. The waveform is very different from a normal tectonic earthquake. And then after that, there's this. I also mentioned this seismic signal that comes from the seiche. So what AEC has done a lot of work on is detecting the seismic signal from that catastrophic failure. So this is the big one. That makes it easier to detect, but it's actually still a fairly new technical development. It's actually only about, a year and a half old for AEC to be able to automatically detect these. And And part of the application of that is that they would then interact with the Tsunami Warning Center, part of NOAA. And so if you imagine, for instance, at Barry Arm, for instance, if there was a huge landslide there, in theory, AEC would detect that within minutes. So ideally, we're hoping for less than 5 minutes. They would be able to get that information, or actually the information would be automatically received by the Tsunami Warning Center. They could then assess, is this something that might actually be a landslide that generated a tsunami, and they could issue an alert in particular to Whittier, which is quite close to Barry Arm. So that concept is somewhat in play. There are a bunch of potential ways that this could fail. So the most obvious one is there's very little time when one of these events happen. You're looking at, for Whittier, for instance, in Prince William Sound, it's about 18, 20 minutes, something like that, between the landslide and when the tsunami would show up. If you were, for instance, on the shoal in North Arm, and even if you had perfect communication with a seismologist who was staring at the moment at the land, at the signal from the landslide, it's probably too late if you're there. You really have, I forget, it's like 4 minutes or something. So that's one big problem. It's also untested. So we have yet to actually see a warning issued as a result of this process. I would argue that it may be an overemphasized approach because of that short time frame. Things like sounding a siren when you only have 10 minutes to do something, there's limited value to that. It can be really valuable. In an ideal circumstance, it could be tremendously valuable, but there are actually very few cases where a siren has saved someone's life. And especially when it's in that kind of a short time frame. Now, so I mentioned these 3 different seismic signals. There's precursory, there's the seismic signal from the earthquake or from the landslide. So that's what I was just talking about. Then there's the seiche. So that precursory signal, that's a very different beast. If anyone had been watching, there was very obvious signals coming from this that would have been detectable even at the seismometers that are 10 miles plus away, that were happening, as I mentioned, up to 6 days before. It would have been really hard to say anything 6 days before, but 5 hours before the landslide, it would have been quite clear that there was a strong seismic sequence coming from somewhere in that area. And 5 hours is enough time to say, hey, maybe we don't know what's going on, but this is a good time to get all the vessels out of these fjords because something might be about to happen. So if we had the kind of monitoring to do that, then that could have been useful. We do not have that monitoring right now. There is no operational system that would detect that sort of information automatically. And this is definitely something AEC is interested in. Jackie Kaplan-Auerbach, who's at Western Washington University, she's interested in this as well, and is actually someone who's worked on this for longer than just about anyone, and she collaborates with Alaska Earthquake Center. Some of my colleagues in Santa Cruz are also, working on this, and we all talk. We're not like trying to hide in our little box and figure it out for ourselves without telling anyone. So there is good collaboration going on around this, but if the same thing happened tomorrow, we'd be caught off guard again. We aren't there yet. And so I think this is a really important topic. Anyway, I will stop rambling, but it's a really important piece to study further and hopefully get to the point of operational monitoring.
Is there one more in the room? I'm gonna let Stephen go. Go ahead. Would you introduce yourself, Stephen?
Yeah, Stephen McKay. I work for the Forest Service. I was just wondering if you could speak a little bit about the risk of Petersburg to earthquake-generated tsunamis.
So Petersburg, by being on the Inside Passage, is much more insulated from tectonic tsunamis. So there of course you can get creative. I'm a disaster scientist, so if you want me to come up with something terrible, I can probably do it. But if we look at the I guess the more common earthquake generated tsunamis, most of these are generated at subduction zones, first of all. And so when you get to my neck of the woods, in South Central Alaska, we have a big subduction zone right offshore. And in 1964, it generated a tsunami that, for instance, in Kodiak was really destructive. So, that is definitely a threat here. In Petersburg, whatever tsunami happened would be coming from further away if it was produced in a subduction zone. It'd be, could potentially be coming from Kamchatka, like the earthquake that happened this summer, or from Alaska or whatever, but it's got a lot further to go. It's going to be a lot less big by the time it gets there. And I don't know the details of modeling of the propagation of the wave into Petersburg itself, but you're quite well separated from the open ocean, and I suspect that the impacts are pretty minimal. Sometimes when you do see impacts in these more protected areas, they are specifically in the harbor. So even a modest tsunami, so say the water level was varying a couple feet, it's not something that is going to really put you in any danger, even if you were standing on the beach. It varies by a couple feet quite rapidly, and so it can generate really strong currents, and this can be destructive in harbors. Now, if you want to park your boat somewhere to get destroyed by a tsunami, bring it down to Crescent City. That is like the tsunami magnet of the entire Pacific. They pick up basically every tsunami that happens is damaging in Crescent City. Petersburg is, way, way lower on the list of places to worry about. There probably are some scenarios that would involve a much nearby earthquake that produced land level change and also ocean bottom change that generated a tsunami. And I don't know of a specific scenario that would be concerning there in Petersburg, but that would kind of fit into a different category there. This would be the sort of thing to be very violent shaking. The direct shaking impacts might be worse than the tsunami if it was close enough to generate a dangerous tsunami. I would more worry about delta fronts failing. So if you have an earthquake wherever, whatever kind of earthquake, if it shakes Petersburg pretty hard, I would worry about something like the Stikine Delta failing. That was the sort of thing that happened in 1964 and actually did the majority of the tsunami damage. Was not related to the tectonic tsunami, but it was related to delta fronts in Valdez, in Chiniga, in Whittier, and in Seward. All those places had delta fronts nearby that failed and produced really destructive, deadly tsunamis. So that's not, the direct tectonic effect.
Awesome. Thank you so much, Hig. That was really, really informative. Really appreciate that. I did record this. I actually remembered. So you want it from me, go ahead and email me, and if you have questions, Hig, you're willing to take emails from whoever with whatever their questions are there at your email address?
I am. Yep. Drop me an email if you want to chat further.
Great. Okay. Thank you.
Thank you all. Sorry I can't be there in person. I'll be through someday, I'm sure.